Good afternoon. Well, almost good afternoon. Can everybody hear me? Brian, can you hear me?
Yeah.
Good. Just so somebody's saying you can hear me, that'll be my first question every time we open up a session. Well, welcome to class today, everyone. And like I said last week, what we're going to do today is talk about some function transformations and some function algebra. Now, if you've looked at the daily schedule, we'll have our first test next week, and that will actually be a WebAssign test. And I will give more information about that towards the end of the week. And there will be, like I say, specific directions for it. And also the window for the test will be adequate enough so that you have plenty of time to make plans. And because I know you have other tests, so there'll be a sufficient window so you can do your work and be comfortable with that. So I'll give you information about that. Now, what I want to do today is pick up where we left off last class. So I'm going to go ahead and share my screen. Now, what I asked you to do last time was just to think about maybe what the transformations were in terms of the shifts. And I'm just going to say that what's on this sheet here as I uncover it will be formulas that you need to know. So make sure as you take good notes of this, obviously we are recording this lecture. One good thing about this is just like identities is to put them on note cards so you have an easy reference. Now, the letters used and the phraseology used with this type of algebra, that is these transformations, can vary. And so I want to be very explicit today about what I plan to use. And I want you to be flexible because as you look on the internet, as you use other books and things, the content will be the same, but lots of times different letters are used and the actual phraseology, like I say, the descriptions can vary, but everything pretty much means the same. So what I want to do is just to let you know about the particular letters I plan to use. In this case, I want to use letters that we're actually going to see when we do conic sections towards the end of the course. Once we finish trigonometry, we're going to go back to algebraic structures called the conic sections. And we've actually already studied some conic sections, but we'll be going into more detail there. So what we're going to do is usually we're going to take f to be the parent function. That'll be a function that you know about. Say maybe a function from college algebra, the x squared function, the 1 over x, the x cubed, the square root of x. These functions that we deal with regularly that occur a lot. And so what we want to be able to do is to transform those types of functions with some very simple rules. Now, when I need a positive number to shift horizontally and vertically, I'm going to use h's and k's, just like you would for the equation of a translated circle. So I will use these letters for the shifts. And then for the stretch or stretching compression, I'm going to use a positive C. Now, it doesn't matter what letter you use. I'm just going to try to stay consistent with these. But you can feel flexible and use other letters if you want to use alphas and betas. I mean, it doesn't matter. What we want is a convenient notation that's easy to replicate. Now, this is where I left you last week, and I want to go ahead and take that idea and extend it to the horizontal shifts. Ladies and gentlemen, we're going to do the horizontal shifts and the horizontal stretch and compression first because those are the least intuitive. And then we're going to work into the other ones that are very intuitive so you can see why we actually do what we do here. Now, what I've listed for the horizontal shifts, the first one, I'm going to use a very short phrase. I'm going to say right shift by H. Now, if we're thinking about a point on the graph of f, x comma f of x, how do we activate, so to speak, a shift to the right by h units? Well, one way to do it is to add for each point on the graph, add h to the x coordinate. that will shift the graph to the right by h. Now, we have to remember this because this is one way of doing a geometric procedure in the x coordinate. Now, because the goal here is a functional equation, this x plus h is good, at least from a geometric standpoint, but we want all of the algebra to move into the function. So what we're going to do, and this is what I was asking you last week to think about, you may have seen this before, you may not. What we're going to do is we would like to be able to relieve ourselves of the h here. So I'm going to make a little change of variable. I'm going to replace x with x minus h. Now, when we do that, everywhere we see an x, we replace it with x minus h. So now we have x minus h plus h. Again, this is not unique. It's one way of getting to the finish line, so to speak. And then this x is just replaced with x minus h. Okay, so now we get an x comma f of x minus h, which is equivalent to this. But this now is a functional equation. This gives us the transformation relative to the function. So I know in college algebra, your professor said, okay, ladies and gentlemen, if you replace x with x minus h, you have shifted the graph h units to the right. And everybody scratches their head and says, that doesn't make any sense. You know, that seems counterintuitive. Well, the problem with the horizontal shifts is that we're moving the x coordinate algebra into the y coordinate. And that's why we get this rather strange functional equation. So again, when we see this, we think this. That is, we see this and visually we move the points to the right by h. So both of these are important, but this in terms of the functional equation is extremely important because again, say you're in a physics class and you need to shift everything a certain number of units to the right. You can do it this way. Again, these are universal equations. You use these in physics, any math course, use these in economics. You probably used these before and didn't even know you were using them, okay? Now, the next one, again, is just like the previous one. So we're thinking, all right, what's going on here? Well, if we want to do a left shift by h, and again, what I'm trying to do here is write phrases that are easy to remember and very compact. So here we're thinking, okay, if I want to take a point on the graph of f and shift it to the left by h, I can simply change the x coordinate. That is, I can subtract h from the x coordinate and do the left shift. So you're thinking, okay, that's basically what we did here. Now, again, in terms of geometry, in terms of a visual, say you were tutoring somebody in this, they say, yeah, that makes sense to me. But then again, we need a functional equation. So let's do the same thing we did here. Let's replace x with x plus h so we can absorb the negative h. So again, x becomes x plus h. So we have x plus h minus h. Well, the h is absorbed and we're left with x. But now the f of x becomes f of x plus h. So again, your professor last term probably said, okay, ladies and gentlemen, if you replace x with x plus h, you have shifted the graph h units to the left. Now that's long-winded. So we just say left shift by h, or you can just say left shift and know that it's h. So again, this is the functional equation which we observe and say, okay, that's a shift to the left. How do I geometrically do it? I do it this way. So the idea with the horizontal shifts is that they are less intuitive and you have to do a little bit more work to get the actual equation. So now what I want you to do is put these on your formula card. Again, we have a positive h, right shift by h, left shift by h. So that's what I was talking about last week. And again, this is how I teach the transformations in a way to make them algebraically real to you. Unfortunately, sometimes if we just simply think about it in terms of memorization, that might be good for a while, but we need to put this up into the long-term registers so we can call on it. Now, let's look at the next one. After this one, they'll be easy. And I always say that, I'll just say they'll be less challenging. That's probably a better word. Students always say less difficult, Professor Ron, not easy. And I agree. So the stretch and the compression horizontally, we're going to look at this the same way that we looked at these. That is, first, we're going to start with a positive A, which is bigger than 1. And so you're thinking, well, I want to stretch all the points uniformly. I want to stretch in the horizontal direction. So how can you do that? Well, you can multiply the x coordinates by a number bigger than 1. So you multiply by 2, you stretch by a factor of 2. You multiply by 3, you stretch by a factor of 3. Okay? So you're thinking, well, this is good. That reminds us of this. But again, we want the algebra in the y coordinate as part of the function so we can get a functional equation. So here's one way to do it. Like we did here, to get rid of the h's, we want to get rid of the a. So we're going to replace x with 1 over a times x, because now the 1 over a times the a's will absorb. So you're thinking, I get it. So now that's an x, and now we have f of 1 over a times x. But you're thinking, that's not exactly how it looked in college algebra. Now at this point, we say, okay, we're going to assign c to be 1 over a. Now think about this. If a is greater than 1, 1 over a would have to be between 0 and 1. So now we see that c is between 0 and 1, and we replaced x with c times x. So again, your brain switches on and says, not very intuitive. So if we replace x with c times x, when c is between 0 and 1, we actually stretch by 1 over c. Now, sometimes when these are written and you're supposed to just apply them, the phraseology may be a little bit different from here. But what I'm saying is if we have a 1/2 x, c is 1/2, then we stretch by a factor of 2. That is, the x coordinates get 2 times bigger. The idea is very, very counterintuitive, but it's what you learned last term. Now you can see why it works. That's what we do in pre-cal. We step it up a little bit so we get a better understanding. And we're going to do this in calculus all the time. So we need to start getting used to making a variable change, or at least recognizing when we do it. So put that on your note card. And again, I'm sure your professor last term waited to the very end to say anything about this, if at all, because again, very counterintuitive. Now, let's look at this one. Now, after doing these two, you're going to become professionals, and you can share this with your friends who just don't want to believe them. Now, if we want to make the compression in the horizontal direction, that is, we want to make the x coordinates smaller, we can start this way. Let's just assume that we have a positive number that's between 0 and 1, like maybe 1/4, okay? And so when we multiply the x coordinates by 1/4, we make them smaller. We compress, okay? All right, so let's see. What's the functional equation going to look like? Well, we do the same thing we did up here. We replace x with 1 over ax. And then, again, the 1 over a times the a here will absorb the a's, and you're just left with an x. And then we have the same situation here. But in order to make the equation a little bit neater, we're going to let c be 1 over a. But here's the thing. We have the opposite of the last step, or the last case. If a is between 0 and 1, say it's 1/4, when you reciprocate it, you get 4. So when you reciprocate a, you actually get a number that's bigger than 1. So now you're thinking, wow, here we go again. If I replace x with c times x, when c is bigger than 1, like 4x, that's going to compress the graph by a factor of, in this particular case, 4, because everything's going to be 4 times smaller. Now, just remember, whether they reciprocate in the phrasing or not, just remember, when you stretch, you make things bigger. When you compress or shrink, you make things smaller. So be sure that's what you're doing. Every book will have some kind of phrase or whatever to express things, and they won't be exactly the same. That's an unfortunate thing about math, but the majority of what we do is universal. So just relish the fact that when you learn math here, you can go to Europe and do the same math and everybody will understand you as long as you just write math. I mean, you want to go to France, I guess you need to learn French, or if you want to go to Spain, you need to learn Castilian Spanish. I mean, whatever, you know, I've always wanted to go to Germany and tour all the churches where Bach composed his music. I got to learn some German if I'm going to get anything out of it. Now, let's look at this. We've done the difficult ones, so I want you to put these on note cards. Now let's look at the easy ones. And when I say easy ones, what do I mean? Less difficult. Okay, so when we do the reflections in the x-axis and the y-axis, so we've got the x-axis and we want to reflect a curve. We want the x-axis to become a mirror. So we're going to make all of the y-coordinates, all the values of the function, they're negatives. So when we think of the transformation, it's just x comma negative f of x. That is, we apply the negative to the entire function. We distribute it. And we've practiced a lot with distributing negative signs. We're done with that one, because we see the algebra is related to the function. So that's the functional equation there. We're done. So isn't it nice when that's it? That's the vertical deals are always simpler because they're already tailor-made. You don't have to make any change of variable. They're ready to go from the beginning. Now, so what if we're thinking about reflecting in the y-axis? So we've got the y-axis here and we've got a point here. We want it over here, the same distance away from the y-axis. Well, we think like we thought up here. We just replace x with its additive inverse. So if we've got 2 as the x coordinate here, we'll replace it with -2 to move it equidistant on the other side of the y-axis. Again, that's fine, but that's not like this. So how do we get rid of the negative? Well, we replace x with its negative. So the negative of x gives us the x, and now we've got, yeah, we remember college algebra. Replace x with the additive inverse of x, that gives a reflection in the y-axis, or we say y-axis reflection, because we're lazy. So this one, very intuitive. This one's like these here, not as intuitive, but at least you can see here that this makes a little bit more sense, at least in terms of moving to the other side of the y-axis. So again, now that we see these don't look so bad. Now, for the vertical, I saved them for last because they're the easiest ones. Now remember, I'm going to use K here for the vertical instead of H that I use for the horizontal. Now, if we want to do vertical shifts, that is, we want to shift the graph upward by K, we just add K to the Y coordinate. So that one's done. No more there. That's done. So if you like, I can put a box around this. I can put a box around all of these. They are done. So if we're thinking of shifting the graph downward by K units, like 4 units, we subtract 4 from all the Y coordinates. So f of x minus K, done. Downward by K, upward by K. V shift by K, upward or downward V shift by K. Use as few words as possible to give you a description of what's going on. So again, very intuitive. No work required here, just like this one. Now let's think about stretch and compression vertically. So this is very intuitive. So you're thinking, if I want the Y values to come out bigger, then I'm going to multiply the Y values by a number bigger than 1. So if C is bigger than 1, I can affect that transformation by replacing the Y coordinate with C times f of x. And that's done. Likewise, if I want to compress vertically, I can multiply the Y coordinate or the function value by a number between 0 and 1, say 1/3. So the idea here is these you could understand as a, 6th grader or a 5th grader. You would understand these if someone said, okay, believe me. But now you can see that the counterintuitive approach that we have to, or the results that we have for horizontal, are based on the fact that we have to move the algebra into the function. And that changes things in a way because we have to undo something. So it looks like we're doing the opposite of what we're actually doing. So again, when you put these on the note card, put them into the long-term register. So every time you see them, you snap right into context and say, okay, this does this, this does this. Now, one thing I want to do is to take these transformations and apply them in succession. Now, I can tell you to apply in a certain order some transformations. That's relatively straightforward. But when you have to actually undo something, in the sense that I give you a function and say, can you give me a graph of it without having to plot 20 points? So we're going to start out in this case with a parent function that's simple, because we're going to do more of this at the end of the week when we talk about quadratic functions. So we're going to have a parent function will be x squared. And what we want to do is stack the transformations. And what that means is what we're going to do is apply in succession. Apply in succession. Now, often students find this the most difficult because they're like, well, Professor Ron, I don't know what the parent function is. Well, rest assured that we'll focus on plain old x, x squared, square root x, x cubed, absolute value of x, 1 over x, and it's time for a new pen. Yeah, that's what's good about Amazon. You never have to worry about running out of pens because they'll send you a whole box. 1 over x and maybe the cube root. So these will be parent functions that we're used to from college algebra. So if I ask you to graph something by transformations, I'll stick to a good parent function that you know. So don't worry that it's going to be something, that you've never seen. So we're going to just call the new function this, and this is going to be a shout out to what we're going to do on Thursday. So I wanted to give you 2 ways to do this. Now, when you look at this new function, you see that this is quadratic and the square is completed. We like that. Completed squares are nice. So we see here that the parent is indeed x squared, but we've done some transformations to this. And ladies and gentlemen, we realize that the completed square allows us to actually unravel the function. And if it's not given in completed square form, we have to complete it because you can't make up the transformations. We only have the 6 that I just mentioned. Well, the 5 basically with 2 parts. and we have to stick with those. So what we want to do is graph the new function in the sense that this is new, the new function. Now I'm going to do a little bit of extra work. I'm going to go ahead and do the X and Y intercepts just to get some practice. You know about these. I just want to do some extra practice, but basically we're going to take 3 simple points from the x squared function and move them. Now, what we want to do is stack the transformations. So when we look at starting with the parent, we start on the inside and work out. Notice x has been replaced with x minus 2. So we say x minus 2 squared. Then we go back to our cheat sheet, and that's a right shift by 2. So we just write it in, right shift by 2. I do a lot of these in the practice tests. And so you can go through those and look at what those amount to. Just a lot of practice. You can make these up. Now, again, when we move the points, we'll have to remember to add 2 to the x coordinates because we know that this is a right shift by 2. Now, let's just work out. We have a 1/3 there. So we're multiplying the function by a number between 0 and 1. So this is a decompression, vertical compression by 3. That is, we're compressing it by a factor of 3. The coefficients in this case are going to be decreased by 3. Now what we want to do is write that down so we get 1/3 x minus 2 squared. Now let's look here. We move out a little bit more and we see the negative sign. So we've slapped the negative, so to speak, on the function. That's going to reflect in the x-axis. So we say x-axis reflection. So now this gives us negative 1/3 x minus 2 quantity squared. And now the last one, we see that we've added 3 to the function. So here's the function now, that's the new function. We get a newer function, and now even a newer function. And then to this function, we add 3. So this will be an upward V shift, upward V shift by 3. So the idea here is that we just want a simple roadmap from one function to the next. Now, you might say, okay, well, you know, I could plot 500 points, but that's not a good way to do it. This is a function we know about. It's got a vertex, and it has some simple points. And so now what we can do, if you will, let's go ahead and move them. So we've got the vertex 0, 0, and we're just going to move real easy points, 1, 1, and negative 1, 1. Now when we do that, we can apply each of these. That is, we've stacked the transformation. We apply in succession. So the first is we do a right shift by 2. So we add 2 to all the x coordinates. So this gives us 2, 0, 2 plus 1, 3, 1, and then 2 plus negative 1, that's a 1, 1. So now we see that we use both interpretations of what's going on with the horizontal shifts. Now we do V compression by 3. So we're going to make the y coordinate smaller by a factor of 3. We're going to divide by 3, so to speak. 2, 0, 3, 1/3, and 1, 1/3. So you're thinking, not only do we have to know what the functional equation does, we have to know how to apply it in a geometric sense. So far, got that. We got that. Now we want to do the x-axis reflection. So that means all the y coordinates will become negative of what they are. Well, zero negative, negative zero doesn't change. So that's easy. Now we take the negative of 1/3 and we take again the negative of 1/3. Now, the very last one is the easiest one. That is, we want to add 3 to all of the y coordinates because we have an upward v shift by 3. So now what I'm going to do, I'm going to write 3 with the denominator of 3. Just say 3 equals 9/3, just to get a common denominator. So now when I add, we're good to go. Now, the first one, well, I don't need it. We'll just have 2, 3. So we're shifting the point upward by 3. Now here we have 9/3 plus a negative 1/3. So that gives us 3 8/3. Here we add 9/3 here. Again, we get 1, 8/3. So now this is the new graph. Points on the new graph. Points on that graph right there. Now, one thing I want to do before we plot these, because we know what this is shaped like. We know the shape of this, and this was obviously going to open downward because of the negative here. But let's go ahead and just get the x and y intercepts just for some practice. That's always good when we're taking the first test. So let's do the x intercepts. So when we find the intercepts of a function, we just set the function equal to 0. So we have 3 minus 1/3. This is just extra. You don't have to do it, but I just want to give us some practice with this. So now, of course, we can take this term over and then flip everything around. So we get 1/3 x minus 2 quantity squared equals 3. I always like to have the x's on the left, but you can put them over here. But I took this over and then did the mirror image of it. Now we can solve for the square by multiplying by 3. So we get x minus 2 quantity squared equals 3 times 3 or 9. So now we have the square root property. So x minus 2 equals plus or minus the square root of 9, which is 3. Again, very simple, but very important. I mean, we don't have to do as much number theory as we did last week. We had all those numbers to factor, and this is actually less work. So now we get x equals 2 plus or minus 3. So we'll have x-intercepts. We'll add 3, we get a 5. And if we subtract 3, we get a negative 1. Just to get some extra points, that's all. Just to make it a little bit, make the graph look a little bit nicer. You know, you can draw it and then you're like, well, you know, if I'm going to cross the x-axis, I can kind of get a ballpark figure or not worry about it at all. So now y-intercept. So these would be the points on the x-axis, at least the tick marks, where the graph would cross. Technically, that's an intercept. We often think of intercepts written as points, but technically these are the x-intercepts. Now, the y-intercept we just get by replacing x with 0, so that's easy, and that's clearly in the domain. So y of 0 will be 3 minus 1/3, and let's replace x with 0, so that just gives us a negative 2 squared. So we get 3 minus 1/3 times a 4. So this will, and let's go ahead and write this with a denominator of 3. Sorry, I make the resolution a little bigger. I gotta remember to move the page up. So now we have 9/3 minus 4/3, which gives us 5/3. So what I want to do now is just go ahead and get a nice simple plot of these using these points. Go ahead and spread it out a little bit. The WebAssign will just usually give you plots and you have to choose, but you certainly should be able to work it out. Now, what we can see here is we've got like 1, 2, 3, and then we've got a -1. So we can spread this out a little bit, and then we get that 5. So -1, 0, 1, 2, 3, 4, 5, just to spread it out because we can. Otherwise, we have to be a lot more creative. And then for the y-axis, let's see, 1 to 3 basically. So we'll 0, 1, 2, 3, and we'll just go ahead and guesstimate here about, that's what, 2 2/3. So we're about right here for 8/3. And then 5/3, the same thing, down by 1, about right here. And then of course, we've got the intercepts, -1, x-intercept, that's the y-intercept. And then 1, 2, 3, 4, 5, there's another x-intercept. And then these points here, which are really the most important ones, that the vertex now becomes 2, 3, which you can see from the completed square form. So 2, 3, there's our vertex. And then we have 1, 8/3. So I'll use this point, 1, just kind of eyeball it. Now this doesn't have to be a work of art, just something reasonable. And then 3, again, just kind of eyeball it. So we can join these. So when we think about the graph here, we think, well, this is minimal work. I mean, what's nice about this is now we can say, without doubt, that's the new vertex. The transformations take the vertex to the new vertex. And then we get these new points here. And we know the shape of the function because we know the shape of the parent. And then just to make the graph a little bit better, we go ahead and figure out the y-intercept here and the 2 x-intercepts, just for added detail. But this would be more than enough. I mean, you know, when you draw it, it's always nice to kind of know where things cross, or relatively, you know, in a way where we could say approximately these are the intercepts. So what I want you to glean from this is that it's easy to apply a transformation. Someone says, okay, shift to the left by 1. So you replace x with x plus 1. Those types of problems are simple. You just apply the transformation and are good. But when you have to take a function and unravel it, that's where you practice your algebra and you practice identifying the transformation. So I want you to work through this because in time, when we get to trigonometry, there may be some instances where we will apply this technique and we'll do as much as we need, but we can get some really convenient graphs without having to plot many points, and the points that we have are very useful. What we're going to find with the trigonometric functions is that they're going to be periodic, and so we will only have to graph one period, so as opposed to, you know, doing lots of work. So again, I want you to think about what you did in college algebra and add a few of the ideas to that understanding that you already have. Mainly, I want you to know the actual transformation rules so that when you see them, boom, you do exactly what you need to do. The idea here is I don't want you struggling with the transformation. Get those on a note card and put them up here, get them in your long-term register, and you'll be in good shape. Now, one thing that I want to do before we move on to the function algebra is to talk about even and odd functions. So like I said before, the WebAssign will give you lots of practice with the transformations. Some will be really easy. Some will be more complicated, but I want you to take the example that I did and if you get bored, make up your own. Now, one thing that we find to be useful when it comes to dealing with functions is the definition of even and odd. Now you did this in your college algebra course, but every college algebra course treats even and odd differently. We need to know even and odd for trigonometry. And then of course, when you get to calculus, even and odd will have a bearing on derivatives and Riemann integrals. So we want to know about it. So let's start with this. The function, and you probably already know this, I just want to fill in the detail. The function f is even if and only if. And there are two rules. If x is in the domain of f, and I'll use the shorthand because we're going to be lazy. If x is in the domain of f, then that means that its additive inverse must be in the domain. What this is saying is that the domain is symmetric relative to zero, symmetric to the zero on the number line. So if you have 5, you have -5. If you don't have 2, then you don't have -2. That's how you get the symmetry. Symmetry is required here. And then 2, we replace x with its additive inverse. And you're thinking, well, that does a y-axis reflection. Well, if it's even, this will mean that the function does not change. So you're thinking, got it. If a function is even, then it must have y-axis symmetry. So graph has y-axis symmetry. Now, when I say that, you could draw a function that's even and try to show that it has the y-axis symmetry. But if you look at a graph and say, well, that looks even, you know, that's not a proof. I mean, you could be utilizing the fact that you know more information, but if you draw it, then it must have some y-axis symmetry. It has to if it's even by definition. But remember, the picture's not the proof. The picture kind of helps us organize our thoughts. Now, the other one is the odd function. So again, even. Now, I hope you remember this from college algebra. If you don't, then okay, well, good. I won't put a 1 there. I'll just leave the 1s and 2s over here. Now, let's do the same for odd. The function f is odd. Now, these are very restrictive. These are restrictive definitions, so most functions would not have this quality. That's a lot to ask for. Number one, we get the same thing. We want the domain of f to be symmetric relative to 0. So if we have x in the domain, we must have its additive inverse. And 2, how does the function treat the additive inverse of x? Well, if it's odd, the negative actually factors. So you're thinking, okay, if that happens, then I must have origin symmetry. Origin symmetry. And I'll write it here, graph has origin symmetry. Now, just to kind of give you a good example of each of these before we do an actual example, let's just think of our favorite even and odd functions. We did one on the last one, x squared. This will just give you something to put in your back pocket to say, oh, here's a good example. 0, 0. I'll spread this out. 1, 1. -1, 1. So the function f of x equal x squared, that's our handy even function. That is, you have, the picture should possess the y-axis symmetry. So what that means, as you take a point and you cross through the y-axis, the distance from the point to the axis on either side should be the same. That means that the y-axis is a symmetry axis, okay? So that's what I want you to think of when you think of the prototypical even function. We say even, f is even. So that's a good example to remember. And now, of course, the odd function, we'll just take the cube root function. That's easy to draw. Of course, y equal x, f of x equal x is a nice odd function. So we'll do the cube root that has the vertical tangent at the origin. Vertical tangent. So now what we're thinking of in this case, if we have a point here, we have a point on the other side of the origin, equidistant. So if we think of drawing a line through the origin, this distance and this distance would be the same. So we would say f of x equals x to the 1/3. F is odd. Now, again, this is not a proof, but we expect the origin symmetry to look like this. As you just draw a line or shoot a line through the origin, you'll hit a point on the graph on the other side of the origin, equidistant, the same distance here as you have here. So just like you have the equidistances here, you have the same thing here. So again, this is y-axis symmetry. And we call this origin symmetry. Maybe it's just helpful to have pictures of these, but we really have to rely on these definitions to actually prove that a function is either odd or even. And then, of course, it could usually be the case that it's neither. So, I mean, let's face it, these are very restrictive definitions. So most functions don't fall into either of these categories. So, you know, we don't want to think that we have a perfect world. I mean, we're glad when we have these because they do make our life easier. Now, here's an example. For instance, say you have this, and then we'll talk about some function algebra. But that's what we're doing, right? So say we have f of x equals 3x over x squared plus 1. Okay, and so what we want to do is say even, odd, or neither. So when you look at this, you're like, okay, I'll just go up to the recipe here and figure out the domain, make sure it's symmetric relative to the 0, to the origin, and then I'm going to check out f of negative x. So again, this is the litmus test here. I'm not really sure why it's usually historically the case that students have such an issue with even and odd. These are definitions. And so you embrace this like you do the function transformations and use them. So there's nothing to miss. You just accept the definition. So now, what's the domain? Let's do number 1 here. Well, this is pretty simple. We have no radicals, and then of course x squared plus 1 is never 0. I mean, that only has imaginary zeros. So for real input, any real input, this has real output. So this is all reals. So that was easy. That was less difficult, I'll say. Again, we look for rational expressions that have zeros in the denominator. If this x squared plus 1, we just remind ourselves that x squared plus 1 does not equal 0 when x is a real number. It would have to be plus or minus I, the imaginary unit, as you well know from college algebra. So of course that's symmetric with respect to the origin, so we get that for free. And then two, we just want to look at f of the additive inverse of x. What we're going to find with a lot of these reviews is that we have a lot of definitions, and there's not as much tedium with factoring that we have with word problems and number theory and things like that. You know, when we have common denominators that are just go on forever, so to speak. So now we say, okay, let's replace x with its negative, with its additive inverse. So again, following the definition. So let's do the same in the denominator. So now, of course, the negative factors. So we have negative 3x. And then, of course, squaring the negative, the square of negative 1 is positive 1. So we get x squared plus 1, just using properties of real numbers. And now, of course, when we have a fraction and we have a negative in the denominator or the numerator, we can just pull out that negative to the side. So this will just be the negative of the fraction 3x divided by x squared plus 1. But of course, 3x divided by x squared plus 1 is the original function. So we do get the negative of the original function. So we go up here and see that 1 is true and 2 is true. That is, by definition, f is odd. So by definition, f of x is odd. So that's a proof, really. That's a proof right there. When you solve an equation, you're really doing a proof. Everybody says they don't like theory, but it's not true. You do theory every time you do a math problem. I mean, the idea is what we try to do in pre-cal is build our foundation a little, give more substance to the foundation so we have an even better understanding as we move into calculus. So you're going to have opportunities with the WebAssign to practice some of this. I don't think you'll find even and odd difficult. What's so good about the even and odd is the fact that you get this nice symmetry here, and with that, maybe less work. As we continue in our math courses, we will find even more uses for even and odd. Fourier series are based upon the even and odd nature of sine and cosine. So the use of these types of functions is all over mathematics. I mean, we, again, and as your STEM career continues, you'll see more of this. So that's one reason we want to be able to say something about these important functions. There's so many good topics in math. We have to hit quite a few of them to get you ready for calculus. Now, what I want to show you first is just a couple of definitions here. And this is like what we had at the beginning, but this is really simple in the sense that you already know this. We've been doing this all along. And what I've written here is algebra and compositions, combining functions. This is 2.7. So, of course, here, where we got function algebra, we suppose f and g are functions. Okay, so when we look at this, you're saying, well, you're writing all this stuff over here to the right, you know, do you have to do that? And I'm like, the answer is no, because really we know that. But what I've tried to do in this definition is to emphasize what should be apparent to us. So I've entitled this function algebra, and you did all of this in college algebra. Now, what does it mean to add two functions? That is, symbolically, if we want to add function f to function g, we call that the sum, and we write it f plus g of x. Now, f plus g of x. So we're thinking, okay, shouldn't we just add all the outputs? Exactly. So we define this to be f of x plus g of x for all the x that makes sense for f and g. And you're thinking, okay, well, that would mean all the inputs that are in both domains of F and domains of G. So even though I've written this here, it should be evident that that is the case, because we have to make sure that both of these, at least in our class now, are real numbers. And if X is not in the domain of F, that would not make any sense. So here we've written this just to remind ourselves, intersection. And of course, with intersection, you think and. That is, X is an element of the domain of F, and X is in the domain of G. It's an element of both sets. So written here, but again, it should be apparent that that is the case. Now, the other three are very straightforward. Again, when you take the difference of two functions, you call it F minus G of X. How do you define it? Well, you define it just like you do the sum. You say for each X in the domain of F and the domain of Y, we define the difference to be F of X minus G of X. Again, very simple, but very important, because when you start learning theorems about limits of sums, limits of products, or derivatives of sums, or derivatives of products, you must be able to define them the way we've done here. So right now it seems like just busy work, and maybe so, but this will have a great impact as you work through calculus. You might say, if we can integrate F and G, they're Riemann integrable, would their sum also be on a particular interval? And you would prove that the answer would be yes. So we need to know these definitions. And for now, we can rest assured that like the even and odd, we'll see more of these in our future. Now, the product, we get kind of lazy. When you talk about the product of two functions, you just juxtapose the letters that represent them. So we'll say FG or F times G. So the product function, F times G of X, is just F of X times G of X, just like we've defined here, of course, where X is in both domains. And then we call that the product. The quotient, we're basically thinking of a fraction or a ratio of two functions. We'll say F over G, the quotient of F and G. Again, we define new functions from old functions, so to speak. So the quotient function will just be defined as F of X divided by G of X for X in the domain of F and X in the domain of G. Now, of course, what I've written here is like what I've written here. We don't want to divide by 0, so of course we would exclude G of X equal to 0. So any X that would make this true, we would kick out, because again, it would not be defined as a real number. Division by 0 is undefined. So all of this is extra. We should know this, but history proves us better if we go ahead and write this down and think about it. Now with the composition, we're going to figure it out without doing this. But for these are really, really important. And most books make the effort to write down apparent things. Again, just remember that whatever we put over here must make sense. And so we must have elements in both domains for 1, 2, and 3, and 4. And then, of course, we must be careful to not divide by 0 in the quotient. Now, what I want to do is an example that has to do with a difference. For instance, let's apply that. So now we have the following example. That is, we have F of X, and we'll have to use some other letters since the WebAssign used F. We'll use maybe a G and an H. So we have F of X equals the square root of X plus 3 minus the square root of 9 minus X divided by X. Now, what the problem in WebAssign says is compute the domain of F. Now, when we look at this, we see that this is just a difference of two functions. By definition, F is a difference of two functions. So what we can do is define, I'll just do it this way. This will just equal g of x minus h of x. That is, g of x will just be the square root function. And we'll just call h of x the algebraic function square root 9 minus x divided by x. So we had to choose another letter here since f was already taken. So equivalently, the domain of f will now be the common domain. The domain of G intersect the domain of H. And of course, when we do the domain of H, we'll have to make sure we don't divide by 0. So if we want the domain of F, we have to make sure that all elements here are in both of these domains. So this will make sense. So again, obvious, but you know, you've got to think about it, and it's good to write this down. So we're seeing that this is a difference of two functions. So now let's go ahead and write it. So the domain of G, that'll be all x. We're assuming real, so we won't put element of R, just write down a little bit less work. X plus 3 is non-negative. So we know that we have to take square roots of non-negative real numbers if we want the result to be real. But then, of course, this will just give us x such that x is greater than or equal to -3. I went ahead and wrote that out, even though I think you know that. So this will just be an interval notation. And remember, WebAssign likes intervals. And so if you don't type an interval, it'll mark it wrong. So be sure when they request interval that you type interval. I want you to get credit for your work. And then, of course, I'll go back and check now that I've had extensions and stuff and all kind of come to an end. I can go ahead and start looking at your work and your quizzes. Now, this again is just like what we did last week. So that takes care of that. Now, what we want to do is think about what we have here. So what about the domain of H? Well, first off, we see that the part up here is going to give us a few issues. That is, we first need all x such that 9 minus x is non-negative. That is, we can't do this problem the way it's listed unless we verify what we need from here. So now this will be all x such that x is less than or equal to, just take the x over and take the mirror image, less than or equal to 9. But now we can write that as an infinite set, negative infinity to 9. Now, when we look at this and we think about this, this is an interesting situation. We're thinking, okay, well, now we've done this, but then when we look back here, if we have a quotient, we've got to make sure that we don't divide by 0. So we see we've got an x here. So additionally, x is non-zero. If we don't want x to be 0, x is non-zero. I mean, it's like, okay, we got that. So now, what does this imply? So this implies, equivalently, the domain of H will now be, again, real numbers, negative infinity to 0, exclude 0, and then 0 to 9. So we get negative infinity to 0, parenthesis, union, again, parenthesis 0 to 9. So we have the two pieces now. Now we need to see where they overlap. That is the common. So we've got this for G, and we've got this for H. Now, there's a little rule that we can use here, and it's called the distributive law, because we're going to intersect this, and I want to show you that. This is called the distributive law for sets. You don't always have to use it, but it certainly kind of keeps you honest when you do these. If you are thinking about sets, we can say A intersect B union C. This is like multiplication distributing over addition. If we think of intersection as multiplication and union as addition, this will be A intersect B union A intersect C. So that's just a simple distributive law that reminds you of what you do with multiplication distributing over addition or subtraction, as the case may be. So now we'll do it. So we say domain of F will now be, again, G domain, -3 to infinity, intersect, and I'll use set braces, negative infinity to 0, union 0 to 9, brackets. So now what we do is we do this part. We intersect the -3 to infinity with negative infinity to 0. Well, this is kind of odd when we look at this. We see this has a few negative numbers in it, -3 up to 0, but then after that, this basically stops at 0. So we can include -3 up to 0 with a brace, with a parenthesis. So let me do this. Let me go ahead and write it out in 2 steps. Let me go ahead and do exactly what I've done here. So this will be -3 infinity. Sorry, infinity never gets a bracket because it's not a number. I just want to go ahead and write this out with the notation that I've used here. Intersect union -3 to infinity, intersect 0 to 9. And so we can use the same technique that I just used before, but I wanted to go ahead and write this out using these symbols here. So now we can do what I just said. This will take us from -3 to 0, because this only goes as high as 0, doesn't even include 0, and certainly no positive numbers in this. So when we do the first intersection, we only get this. And then we have union here, union. And now here we do the same thing. Notice this has some negative numbers. This starts at 0, so it has no negative numbers. So this will give us 0 to 9. So this basically, this set here is contained in this set. It's the so-called contained set. So the intersection would just have to be that. So this will give us 0 to 9 bracket. Now, when you look at this problem, again, you don't even have to think of the distributive law so much. But you have to think, how do these sets intersect? And you could do that in a kind of visual way if you want. But if you think about it this way, the visual and the set theory kind of come hand in hand. And you can just analyze each of them. You can say, well, how does this one compare to this one? You get that. How does this one compare to this one? You get that. And then you stick a union symbol. So what I want to show you is that even though the actual algebra that we do here is not very difficult, basically what we're doing is following definitions or the difference of two functions. And then we follow the definitions. Okay, how do we compute the the domain of G? How do we compute the domain of H? So there's a problem within a problem. So again, you never look at a domain question and think that it's simple. You just simply do each step and do it to completion. Again, this will be a new formula that you'll use again. A lot of you may go on to get, maybe if you want to decide to own an engineering firm, you get an MBA, you'll take more probability. But this is also part of real analysis too, which is very important. Okay, now, so that's a good example. So what we want to do at this point is continue on with what we call the composition. Now, one thing that I've noticed here when we do these types of problems is that when we think about compositions, what exactly is a composition? So let me get that out. Or a clean sheet of paper. So I want to write this in a way to give you, again, the phraseology, so to speak. I wish it were all consistent, ladies and gentlemen. I wish that everything we did, everybody said the same way. But I'm particular about how I state things, and not everybody is always that particular. So let's start out with the definition. So suppose f and g are functions. So we want to combine functions in a different way than what we've been doing. So suppose f and g are functions. We'll have a good time on Thursday. We'll do one-to-one, and we've already worked about solving for x, and then we'll do some quadratics. So I think you'll enjoy the topics. These are good review topics. Just good that we review. I mean, just remember that this is review. So we're adding a little bit more spice to make it mean a little bit more. So suppose f and g are functions. So the composition of, usually we write of f with g. Sometimes there's an and, but normally we want to say the composition of f with g. And if there's an and, that's okay. But this pretty much says that f will be the outer function and g will be the inner function. And we're going to say, what does this mean? Well, it is this. We're going to notate it this way. We're going to say f circle g of x, like we were doing f plus g of x, like a sum. But now we have a circle there. Now, remember, this is not a dot. That's not multiplication. This is a circle, okay? So don't think of that as times. When we do multiplication, we just do f juxtaposed with g. Always look at the context, because notation will vary from book to book. And I don't want you to read something into the problem that's not there. How do we define f circle g? Well, we basically substitute g of x into f. So again, what we're doing here is every occurrence of x, whatever its independent variable is replaced with g of x, just like we did when we did f of a plus h. That was a composition, even though we didn't call it that. So you basically substitute one function into another. The inner function is substituted into the outer function. And then, of course, what about the other order? The composition of g with f. Well, again, now the g is the outer function and the f is the inner. So what we want to do is say, okay, well, let's just do it the same way. This will be g circle f. This is fairly customary. The first function that's listed, we talk of as the outer. But usually when you see a composition, it's written mathematically. And so you can already determine that. But WebAssign likes to give you an F and a G and then say, write this and find the domain, or write this and find the domain. So of course, this will be G of F of X. So now what we're seeing here is that when we look at this particular example, can we figure out what the domain is? Because I didn't write it down. And I'm thinking, okay, well, we need an exercise here to say, okay, when we did the function algebra before, I wrote everything down, but I said it should be apparent. Now let's just see here. Domain, let's write this down. Domain of F circle G. Well, let's look here. The X must be in the domain of G, so we can say X element of the domain of G, such that what? G of X is in the domain of F. So that means G of X must make sense if we substitute it into F, domain F. So this is what is apparent if we define the composition to be this. We have to start out with an X in the domain of G, so G of X makes sense. But then we're substituting G of X into F. So G of X must be in the domain of F if F of that's going to make sense. So again, this is probably easier than the last problem. Now let's write it down for this one. Domain of G circle F. Lots of times definitions will make sense to you if you just simply read what the symbols tell you. So now we'll say X is in the domain of F. Everything just switches. And then F of X must be in the domain of G. So I wanted to go ahead and do this to give you an opportunity to think about what is inferred by the definition. Books will be more specific about this and say, okay, well, you realize that this must be the case, just like we realized in the previous example what had to be the case. So it's kind of a smoke and mirrors in the sense that we say, okay, well, if this is indeed going to be a real number, then X has to be in the domain of G, and G of X has to be in the domain of F. And this is all point-wise. And usually we can figure out the algebra that we need in order to do this. So let's look at an example of that. So WebAssign, you know, WebAssign wants you to work, and then they want you to work some more. So some of the problems have more than one part. That's good, but it makes you a little weary at times. But when you get to Cal 1, I want you to know what a composition is. So let's look at an example here. Let's say that we have some examples here. Let me move this chair up a little bit. So here's an example where I'm going to ask you what WebAssign does. I want you to compute the composition and then figure out the domain. So we're going to have F of X will be 1 over the square root of X. And G of X will be a polynomial, X squared minus 6X. Now, if that's the case, here's one of the WebAssign problems. That is, compute F circle G that is, I want a formula for the composition, and also I want the domain of F circle G. Now, every student thinks about the domain differently, but we want to do it so that all the bases are covered. So again, don't worry about not adhering to every step that I do. As long as what's accomplished gets you to the finish line in a legitimate way, that's what's important. So now let's apply the definition. F circle G of X. Well, F circle G of X means F of G of X. That's the definition. And now what we want to do is, well, what's g of x? This is just x squared minus 6x. So let's go ahead and replace that. Now we're back to what we did last week. That is, this is now the input. Everywhere we have an x and f, we replace it with x squared minus 6x. So we only have one occurrence of that. That's in the radical here. So we have 1 square root x squared minus 6x. Okay, so that's the formula. We say formula. Now, of course, if I were giving you discrete values for the functions and not formulas, then we could just play the composition game and figure out values of the composition. But when we have to deal with the formula, the functional equations, it's more work, it's clearly more work. So now we're thinking, all right, we got the formula. How do we get the domain? Well, let's just do what we did before. We know that the domain must live in the domain of G, and the domain of G that we have must live in the domain of F. So whatever output we get for G, it has to live in the domain of F. So we may have to do some restricting. So now the domain of G, start with the inner function. Well, that's just a polynomial. That's all real numbers. So we can't go wrong with polynomials. Again, no division by zero, no radical, so we'll just say all reals. Now, you look at the radical here and say, well, there's no way we're going to be able to keep all of those real numbers. This isn't going to work. So now we apply what we've done here. So then the domain of F circle G will now be, again, x in the domain of G, which is all real numbers. We'll just say x element of the real numbers, such that, and here's the restriction, we go over here. G, that is x squared minus 6x, we're taking the square root of it, so it has to be positive, but we don't want it to be 0 because it's in the denominator, so we need strictly positive. So when we look at this inequality enables the range of G to be in the domain of F. We have to restrict it. We can't put all real numbers into this because this won't make sense. So now what does this mean? So now we get an inequality. Let's write it out, then we'll move from the inequality. X element of R such that X, just factor it, X times X minus 6 is positive. Okay? So that's set theory, and we're done with that because now we need to write the equivalent inequality just by itself and do the BBs. So we get this. And so now we've got our 0 that's built in. We didn't have to work very hard. It was just part of the problem by analyzing this. And then we say we've got BBs will be 0 and 6. 6 makes X minus 6 0, and 0 certainly makes X 0. So now we have a 6 and we have a 0. But this is easy. We did this last week. That's a positive leading coefficient in X squared there, as we see right here and right here. And so we're going to get something like this. That is, these both have multiplicity 1, but you don't have to take my word for it. I always say, just go ahead and take a test point, -10, take a 3, and then a +10, easy test points. And then check the factors. -10, that'll be a negative and a negative for overall positive. So we knew that would be the case. That gets a check. And now, of course, both of these are no good because they make the expression 0, and we can't divide by 0. And then, of course, 3 here will be a positive and then a negative, overall negative. Of course, that's no good. And then if we replace x with 10 here and 10 here, we just get 2 positive. So I kind of do it both ways with the multiplicities just to kind of make everybody feel good about our choices here. So what we're seeing is the composition domain actually became an inequality problem. So when you got a square root and you're doing a composition where you basically make the argument of a radical a polynomial, that can introduce a BV technique. Again, it wouldn't be a problem if this were just a polynomial that was never zero or was never negative. I mean, we could have rigged it that way. But of course, this gives you more work because we clearly know that x squared minus 6x can be negative and can be zero, as we've shown here. So now, well, we're done. So this means, so equivalently, since we kind of did our little sidebar here with the algebra and all, we'll say if and only if domain of f circle G, just follow the checks, will now be negative infinity to 0 union 6 to infinity. So what I want you to see from this problem is there's nothing magical about doing function algebra, figuring out domains. There's nothing magical about doing compositions. You write it down, and then you might look at this and say, if you just treat this as it were, as by itself, if you just start with this, then you can do the problem. On occasion, however, you build the problem from two functions, and there will be differences when you're building the function. So keep that in mind. Again, we want this to represent that we started with the domain of G, and then of course we end with the domain of F relative to the fact that we get real input and real output. So that drives all of what we've done here. So again, look at this as simply following the definition. If you're going to do the domain of a composition, then first you want to figure out the domain of the inner function and then see if the actual output of the inner function is in the domain of F. If it's too big, as it is here, we may have to restrict it. Okay, so that's the key to doing this exercise here. Not difficult, very straightforward, but again, just follow what you already know from your previous work. So that's good. So we see now that as we prepare ourselves for calculus, these types of calculations will come up over and over. And we'll think, like I say, don't think that we leave all of this behind. You take all of this with you, and then you have to even react in a quicker method. So the idea is we want to get as good at this as we can so that when we move into calculus, we have all the raw materials and the tricks and techniques to finish the problems. Now, what I want to do, just to kind of help you out with the WebAssign, there are often problems in your WebAssign where you're given values, and I thought this was an interesting problem. You're just asked to compute values of a composition where you weren't given actual functions. You're basically given a table of values. So I want to just show you how to do this so you can get practice. It's very simple, but it may be new to you. You may have done this in college algebra, but I'm not really sure what you all do. It's such a wide range of application in that class. So we'll have x, we'll have f of x. This is a discrete problem. So what I'm going to do is I'm going to write a little table here. And it's going to have input values, x, and then it's going to have the corresponding values for f and g for the given x. So first what I want to do is kind of cut this in half and then mark these off in threes so I can get 6 columns. So now, like I say, this is a WebAssign problem, and the values of X are 1, 2, 3, 4, 5, 6. You can make up these problems. If you tutor some students, you can make these up. And the values they give us, 3, 5, 1, 2, 6, 5. So for instance, here, we would say f of 2 equals 5. F of 5 equals 6. So here's the input, here's the corresponding outputs for F. And for G, we have 3, 5, 6, 2, 1, and a 4. Now, when you do this, here's what WebAssign said. They said, compute the following. Now, this could be several, maybe 2. Compute F circle F of 5 and G circle F of 4. So let's do that. Now, again, remember, we don't have to use a given functional formula because we're given the values. Of course, here, the values that are given for the input must be in the table if we're going to use this given information. Now, of course, if you're given functional equations, then you can do the same thing. You just have to compute the values. They won't be given to you. So now this will be F of 5. So we go to the table, F of 5 will just be 6. And we finish by computing F of 6. Again, F of 6 is just 5. So that's a fixed point. The composition fixes the 5. We see if we input 5, we get out 5. So that's an interesting result. So G circle F of 4. Again, these are good just to test yourself on the application of the definition of composition. So this is G of F of 4. So now we go up to the table, F of 4 is 2. So we have G of 2. And now we go to the table, we have a 2, G of 2 is 5. Now, again, these are very simple, but I don't want you to get a stumbling block over these. Again, this will clearly work with the functional equations. This is just a little discrete example to just test you on the definition of composition. So again, very, very, very simple, and maybe more tedious than dealing with the functional equations. Now, what I wanted to do is we have these definitions of even and odd. And so you're going to have problems in calculus that require you to utilize the definitions of even and odd to verify or validate certain results in calculus. And here's one that is just an algebraic result. So let's write this down. You'll find these in the WebAssign. And they kind of do these as questions and not as a proper proof, but you get to type in some of your thoughts. So for instance, we'll say, suppose F and G are odd functions. So we want to do something, so we can just call this a lemma. Lemma is usually a result that precedes a major result, but sometimes I just say lemma is like a proposition. So we're going to suppose that F and G are odd functions. Then we want to prove F plus G as a sum is odd. Now, notice I didn't put the X's in, so I'm just kind of doing them with lesser notation. If F and G are odd functions, what this lemma is saying is that the sum is also odd. Okay, so we would need to show that. So we'll say this is a proof. This is the so-called why. When you prove something, you just give a series of statements that take you from the given information to the conclusion, and that can take all kinds of forms. when you're doing math. You've done some proofs probably in your science classes. And and you make logical deductions in your laboratory classes because you do an experiment and then you have to make deductions based on what you performed in the laboratory. And you know that can often be very difficult when you have to have really good experimental procedure and to be able to actually make deductions that are valid. So now when we do this, we'll say, okay, well, what do we have to do? First, we have to test that the domain is symmetric relative to the origin. So we'll say for the sum, we say the domain of f plus g is just the domain of f intersect the domain of g. But the thing is, this is already symmetric relative to the origin, and this is symmetric relative to the origin. So their overlap is necessarily symmetric relative to the origin. So we'll say, then, if x is element of the domain of f intersect domain of g, then the negative must be in there and the negative must be in there because they're both odd. So equivalently, negative x would be in both because by definition, they're both odd. So you get the symmetry by the fact that both of these functions are odd. So if x is in the intersection of both of these domains, which are symmetric relative to 0, then negative x must be in both. So we get that for free. That's like beating it to a pulp. But the idea here is oftentimes when we think about showing that a function is odd, we kind of forget the first part. And really, when you're doing a problem, this is the first thing you have to check. Because if this is not true, then you don't need to go on to step 2. I mean, if the domain was 0 to 5, then stop. That's not symmetric relative to the origin. You've got 3 in the domain, but you don't have -3. So that wouldn't even work. So the idea here is this must always be checked. You can't just assume it. And usually it'll be fine, but you don't completely disregard it. It's not good. So for 2, so we'll just say symmetric relative to the origin or relative to 0, which is the origin for the real number line. Now for 2, what do we need to do? We need to replace x with its additive inverse. So we apply f plus g, in this case, to the additive inverse of x. So now we're thinking, okay, all right, so what does this mean? Well, we go back to the definition like we did the definition of composition. We say, well, what does it mean to take the sum of negative x? Well, we apply f to negative x and we apply g to negative x by definition. So by definition, this is f of the additive inverse of x plus g of the additive inverse of x. Now, sometimes you have to do more work than we're doing here, but this is certainly a good place to start. And now, of course, both f and g are odd functions. So if you have an odd function, then the negative will factor. So this will be negative f of x, and then, of course, minus g of x, because each of these functions is odd. So then you're thinking, well, we've got the -1 here, we've got the -1 here, so we can factor the negative, kind of like doing AC lemma, but numbers are a lot easier. So now we factor the negative, so we get the negative of f of x plus g of x. But f of x plus g of x is just f plus g of x. So this is the negative of f plus g of x. So now, as we work through this, we see that we have a symmetric domain for free, and then we have f plus g of negative x is the negative of f plus g of x. So that tells us that f plus g must be odd also. So by definition, f plus g is odd. Now, the thing I want to impress here is as we move into calculus, like I keep referring to, you're thinking, you know, he's always saying calculus. Well, that's what this course is, pre-calculus. We want to make sure that we at least have a basic idea of even and odd, because when we come back to it, some time may pass and this gets very rusty. So if you can develop some understanding for it early on, it may be the case. And with this type of technique, you can think about maybe, you know, products, differences and things like that, and apply the same technique. And you'll find that it's really, really very simple. Again, not difficult at all. Now, so that covers the function algebra that we need to do and the compositions. Now, what I want to do here is just a simple example from your WebAssign that is kind of word problem oriented, but relatively straightforward. So just as an extra example that we can use, and then I want to say just a little bit about where we're headed. So it says a stone is dropped into a lake creating a ripple that travels outward at 80 centimeters per second. Now, when you think of this, and this is what I want you to think, you drop the stone, and then you basically get the circular ripples. So, like, let me just go ahead. So basically, these are circular ripples. You expect that. The pebble hits the water, or the stone hits the water, and then these just undulate out, making concentric circles. Sometimes we say concentric. That means the centers are the same. The center is the same, concentric circles. Okay, and here's the first question. It says A, G of t corresponds to the radius of the circle. So now this is easy to do. If the ripples are moving out at this point, this implies that G of t will just be 80 times t. That's just, in this case, rate times time. That'll give us the distance. We know D equals RT. We know this too well. Oh my goodness, the Wendy and the bus and the train, and then the Chiron that goes from Tortula to Dry Junction. Numbers, and then numbers, you know, and not fun numbers, not user-friendly numbers. And then B is F of R is the area of the circle. F of R corresponds to area of circle. So in this case, what does that mean? Or equivalently, f of r would just be pi r squared. So what we're thinking here is that if we go up here, we're thinking of this as the radius. So we now can think of a composition. So this implies that f of r of t, thinking of this as a function of, as a composition, we can now replace r of t with g of t, the radius of the circle. So this will be f of 80t. And now in our formula for f, all occurrences of r are replaced with 80t. So we get pi 80t quantity squared. So that'll give us what? 80 times an 80. 8 times 8 is 64, add 2 zeros. So that gives us 6400 pi t squared. Now, the idea here, even though this is an incredibly simple problem, it goes to show you that you're already doing compositions in your science classes. That is, you create new functions based upon the independent variable time. You start out with a function of time, and then you think, okay, well, what's the area of the circle, these concentric circles? Well, based on the radius, we know the area of a circle pi r squared. So we simply replace the radius with the function g of t, which defines the radius. And so basically, we write this as a composition. Even though this is very simple, the composition is basically embedded in the problem. So now we think of, this is basically how things work more so when you talk about science. You've got an outer function and you have an inner function. So this is the outer function, and this is the inner function. And the idea is you can utilize variables that make the statement of the problem simple, and you can use whatever letters you like. Notice I just used R for radius here, but the WebAssign gave it to you this way. It might have been even better for WebAssign just to have called this R of t, and so you don't have the duplication here. So remember, when you're doing science problems and things of the like, be flexible with your notation. Just realize that you are in control of that. When you read a problem, they may ask you to use certain letters. That's formatting. That's what you're well aware of. So if the formatting says use a particular letter, like if the independent variable is x, use x clearly. If the independent variable is t, use t. You might say, oh, Professor Ron, I'm getting this problem wrong. I said, well, you have to use the variable that's stated in the problem. And formatting is frustrating at times, but it forces us to follow directions. And so that's okay. It's not always good when it's 12 o'clock or you've been up for a while and you're really tired and you're trying to get a few problems done. And you see those X's that are red, you just, you can say, all right, I know I'm doing this right. That just really means you just take a little break and, take a nap, go to bed, wake up refreshed, and then you can see things that you would not normally see if you were well rested. Now, we're done with the lecture for today. So I want you to go ahead and think about what we're going to do for Thursday. So for Thursday, we're going to discuss one-to-one functions. So this will be, I want to say this is 2.8. This will be one-to-one functions. Again, you know about one-to-one functions from college algebra and inverses. That won't really be very long. There'll just be some ideas. We've already talked about this to some degree. There'll be some ideas that we need to do, talk about with the definition of one-to-one. And then, of course, the properties that the compositions have when we compose a function with its inverse. Those actually give you equations where you interchange the two functions and the basic output is the same. Just we have to think about the types of letters we use in the range and the domain. That's often a source of confusion with inverses. And so basically what we want to do, if we're interested in graphing a function and its inverse on the same set of axes, we really have to use the same independent variable. And so what we're going to see is that when we do that, we end up with two functions. If you just graph the one-to-one function, you can look at it from a different angle and see the inverse. So one function basically implies the other. We just like as people, as math people, to be able to see both functions, you know, at the same time. And then we're going to see some nice symmetry relationships. And then of course with 3.1, this will just be quadratic functions. Now, we already know a lot of this, but we're just going to showcase the quadratic function as an object of utility and provide some of the characteristics that we know about the quadratic function. We've already been dealing with it, and now we're going to talk about completing the square in a way that gives you the vertex, plotting the quadratic functions, and then possibly using them to solve word problems. We've already figured out that quadratic form is extremely helpful in solving equations. If you can find the quadratic form, then you can apply all of the techniques, the AC lemma, you can apply the quadratic formula. I mean, there's a lot to be had by understanding quadratic equations and quadratic functions. So this will be what we'll do here. So if you have some time to kind of look forward with that, go ahead and read through that, and we'll continue with this on Thursday. I appreciate your attendance today. Again, remember, if all of this is reviewed, that's fine, but study this like you don't know it to get your skill set back up. I think you'll find that there'll be plenty of rewards as we move in to the other topics, even though they will be reviewed. I want us to maybe get a little bit more understanding that we can get. Unfortunately, a lot of the increased understanding won't be there until we get to calculus. Okay, so everybody have a good day and take care of yourselves. Bye.
Bye, thank you.
Bye.
Bye.
Bye, thank you.
Yes, you all have a good day.